Good morning, sir.
Yeah, good morning. Good morning.
Shall we start? A very good morning to our respected dignitaries, distinguished delegates, faculty members, presenter, and my dear students. It's wonderful to
हेलो
have you all.
माइक शुरू करो माइक ऑन करो
My कौन है sir? Sir on है. आवाज आ रही है? I am audible.
Hello.
Yeah. Whether I am audible?
Yes, madam.
हेलो गुड मॉर्निंग प्रोफेसर स्वामीनाथन सर
Yeah, good morning. Good morning. How are you?
हेलो
Yeah, good morning.
Sir, good morning.
Hello. Audible?
हाँ या
It is my privilege and great pleasure to welcome you all for this technical session of the International Conference on Advanced Material Science and Engineering, ICAME 2026. I am Dr. Deepika Brijpuria, Assistant Professor, Postgraduate Department of Chemistry, and I am honored to serve as the rapporteur for this session. As a part of today's technical session, we are privileged to have an invited talk by esteemed resource person, Dr. Swaminathan. Swaminathan on role of biochar in photo and electrocatalysis. And to begin the proceeding, I am respectfully invite our chairperson, Dr. Neha Agrawal ma'am and Dr. Dev Sarkar sir. Dr. Dev Sarkar sir is professor in School of Chemical Science, Swami Ramanathan, Teeth Marathwada University, Nanded. He has 20 years of PG teaching experience with many number of papers of publication in international conference. Citation is 116 and Google Scholar Index is 585. H index is 12 and he has more than research experience 19 years. His thrust area is solution of thermodynamics, thermophysics, properties and molecular interaction in drugs and biomolecules solutions. We welcome you, sir, on behalf of ICAME 2026. Another co-chairperson for this session is Dr. Neha Agrawal. She is accomplished academician, researcher, and author, currently serving as an assistant professor in the Department of Chemistry, Navyug Kanya Mahavidyalaya, with a strong foundation in chemical science and interdisciplinary research. She has made significant contribution to the field of environmental chemistry, nanotechnology, and sustainable development. She qualified prestigious national examination, including UGC CSIR NET GATE in chemical science. She completed her MSc in chemistry with the first division. She has authored and edited numerous scholarly books with leading publishers such as Springer Nature, CRC Press, Bentham Science Publisher, and many more. So we welcome both the chairperson for the technical session, and we invite on behalf of our organizing team, Santaji Mahavidyalaya. Please, ma'am, and please, sir, start the chairing the session.
Hello, Neha madam.
Good morning, sir.
Good
Namaskar.
morning.
Good morning.
Yeah. Do you have the biodata of Professor Swaminathan?
Hello?
Sorry?
CV of Professor Swaminathan?
No, sir. I have not been given that.
Oh, it's a Meenakshi. Actually, the name is Meenakshi Sundaram Swaminathan. So it's denoted as Meenakshi. That.
Sir, I have not received the CV of Swaminathan, sir.
I'm
But
sending.
any,
Gurnale, are you seeing?
Sending. Just a minute.
No, it is, and the name is given as Meenakshi. That.
yes, sir.
Because my name Meenakshi Sundaram Swaminathan, so they have given Meenakshi as that. No, first name it is given as. Are you able to see? I mean that.
Anyways, well, I welcome you, sir, on behalf of the entire team of the conference. And it is my pleasure to welcome you in the conference. And I'm really, I'm taking it as an opportunity that such a senior person who is there, and we all are here to listen to you, sir. And it would be nice to listen to you on the topic of role of biochar in photo and electrocatalysis systems. So I'm extremely sorry at the moment I'm not having the CV, and I was not aware of this particular thing. So I apologize for that, sir. I ask you and I request you to kindly present your screen. At the end of the session, I would like to introduce your CV, sir. Thank you very much, sir.
So shall I start? I mean,
May I request you to kindly present your screen, sir?
so is it, I mean, that visible that?
Yes, sir.
Yes, sir. It is visible.
Okay. So can I start now? I mean,
Yes, sir.
Please, sir.
okay, thank you very much. So thank the chairman for just introducing me. I mean that chairman of the sessions, two chairmen, and I thank Dr. This college, that is organizers of ICA MSc 2026, and also the principal of the college. And I thank Dr. Gurnale also for giving. Is it not audible?
Yes, sir, it's audible.
Audible, no?
Yes, sir.
Okay, thank you. So I thank the organizers for giving an opportunity to present some of the work on role of biochar in photo and electrocatalysis. And it is also, very pleasure to thank Dr. Gurnale also for giving me an opportunity to be present in this ICAMSC 2026. So thank you very much. And I'm actually retired professor from Annamalai University. I retired at 2015. And later on, I am working as a visiting faculty in the Kalasalingam Academy of Research and Education. You can see in that slide, our university, the deemed university, it's a private university and situated in a very nice environment. You can see that university is surrounded by the mountains, which are called mountains of Podigai mountains, or mountains of Western Ghats. And here we have an international research laboratory, and the international research laboratory, one laboratory is their nanomaterials laboratory, where I am working as a visiting faculty for the past 10 years. And here is actually, this place is very near to Madurai, about 60 kilometers south of Madurai. So this is a very nice place to visit. And also another falls, Kutralam Falls, is very near to this place. So thank you very much. And this today I am going to discuss about this role of biochar. Biochar is very, very important. Nowadays, the focus is more on the research on the biochar because it's easily available and it can be tuned for any kind of applications also. So we'll see the role of biochar in the photo and electrocatalysis. Before we see the importance of biochar and its applications, I would like to show some slides on photocatalysis and also on electrocatalysis. So everybody knows about the photocatalysis. Actually, any semiconductor, when excited, by a light equivalent to that band gap energy, then electron from the valency bond is excited to the conduction band. So we are getting two species, reactive species. One is electron, another one is a hole. These two reactive species are very, very important. When they are restricted in the recombination, then we can make use of these two species, electron and the hole. Electron can combine with oxygen producing superoxide radicals, and the hole can combine with or react with water or hydroxide ion producing the hydroxide radicals. These radical species are very, very good oxidizing species, particularly when you take this hydroxy radical is non-selectively degrade any kind of organic pollutant to carbon dioxide and water. So any process that is used by the hydroxy radical is also known as advanced oxidation process. So by using this, we can have the degradation of the pollutant, or the environment or effluent can be even treated by using this advanced oxidation process or by using this photocatalysis. And another one is this electron and the hole can also be used for splitting the water into hydrogen and oxygen. So when you restrict the recombination, like this recombination, when it is restricted, then the electron can produce the hydrogen from H plus ion. This is H plus ion to hydrogen. Similarly, water can be decomposed to the oxygen. So here, this electron and the hole can be used for producing this hydrogen and oxygen or splitting the water. And this is the effect which was long back in Neiman in 1972 was reported by the Fukushima and Honda by using the TiO2, water splitting. And sometimes we see that, photocatalysis is very useful in splitting the water. Actually the band gap energy required for splitting the water is only 1.23 electron volt. But this energy is not at all, criteria. There are so many other criteria. Band gap and band potential levels are more important. So even if we have, and you use photocatalyst having the band gap energy of 1.23 or more, it cannot, all the photocatalysts cannot split the water. Their band potential should be suitable for splitting the water. So here you can see the band potentials of the several semiconductor oxides. You can see that zirconium oxide, potassium tantalate, and francium titanate, titanium dioxide, and all these things. So here you can see that all these, above zero are able to completely produce a hydrogen. That is, split the water into hydrogen because they are more negative. Actually, when it is below zero, they are positive. They cannot give the hydrogen. They cannot reduce the hydrogen to the H plus ion to the hydrogen atom. So all these catalysts which are having levels above zero are capable of splitting the water into, or hydrogen are capable of producing the hydrogen from the water. Whereas at the same time, when the valency bond potential is below above 1.25 electron volt, then it is capable of splitting the water into oxygen. So here you can see when you take wolfram oxide and iron oxide, they are not capable of, reducing the H plus ion to hydrogen. They are capable of only splitting the water into oxygen. So this is actually the band potential levels are more important for splitting the water. Not only the band gap energy decides, but also the band potentials decide about the splitting the water. So if you take a photocatalyst, basic reactions, 3 reaction steps are light harvesting, charge generation and separation, and catalytic reaction. But what are the basic requirements for a catalytic material? Actually, material should have a high surface area or large surface area and a reduced recombination of charge carriers, because when the electron and the hole they recombine, there is no use at all. So the reduced recombination is very, very essential. And again, we cannot make use of this UV light every time. It's expensive. So we should be able to make use of the visible light. So when it is visible light active, then we can make use of the solar light also. So the photocatalyst can make use of the solar light, which is available in plenty, even in our country. So what is the basic requirement? Some of the semiconductors, if you take TiO2 or any zinc oxide, actually that band gap energy is suitable only for the UV light. So we can make this UV active photocatalyst into visible active photocatalyst by modifying the semiconductor oxides. How to modify them? By doping with metals or doping with non-metals or anions, or even coupling with the other semiconductor oxides, or loaded with sulfur active materials like zeolite, activated carbon, and carbon materials. So these are some of these modifications which can be used for making that photocatalyst very efficient. that is increasing the surface area, reducing the recombination, and also making them as a visible active photocatalyst. So when you take the actually these modifications, so many modifications are available, but carbon-based materials nowadays are increasingly used in photocatalysis. Why? Because of their unique properties. They have the high surface area, excellent electron mobility, good electrical conductivity, light absorption, charge transfer, and they are also cost effective because they can be easily available from various sources. What are the common examples of that carbon materials? Earlier, we know only activated carbon, graphite, diamond, and all these things. But nowadays, a number of carbon materials are available. Activated carbon, graphene, carbon nanotubes, carbon nanoparticles, carbon quantum dots, biochar, fullerenes, graphene oxide, reduced graphene oxide, graphitic carbonitrate, so many things, so many carbon materials are available, and they can be used in various applications, including solar energy conversion and environmental remediation. So what are the advantages of carbon-based materials? They are very good adsorbents. Most of the carbon materials are only adsorbents. Actually, they have been used only absorbing material for removing the, these pollutants. But some of the carbon materials are also can be used as a photocatalyst. So they are also removed to adsorption. And in the case of adsorption, what happens is only the pollutants are transferred from one phase to the other phase. It's not at all completely degraded. But when the pollutants are combined with a photocatalyst or metal oxides, then what happens is the adsorption degradation process is taking place. They adsorb and then it undergoes a degradation by using the photocatalyst supported by the carbon material. So the modification of photocatalyst by metal doping, actually this modification by metal doping is costlier, whereas the modification by carbon material is cheaper and more effective also. So each carbon material has unique properties depending on their structural and morphological characteristics. And all these carbon materials, they differ in the carbon content also. So just like, we take two carbon materials. For example, all of us know the activated carbon because this activated charcoal or activated carbon have been used long back from our even UG laboratories. Whenever you want to recrystallize or purify a compound, immediately what you do is you put some amount of the activated charcoal or activated carbon. It absorbs the impurities as well as the material also, so that is removed. So here, activated carbon is completely used. And now, when you compare the activated carbon and biochar, what is the difference between them? This is just to show the difference. Activated carbon undergoes physical or chemical activation to remove tar, opening up high density, and it has microscopic pores. Biochar is simply a carbonized biomass, and it is obtained by the pyrolysis. And activated carbon has a massive surface area well over the biochar. Actually, activated carbon is having higher surface area when compared to biochar, and biochar has a lower surface area, but the speciality is it has a higher concentration of surface functional groups and larger pores, suitable for supporting the soil microbes and also for the supporting the photocatalyst. Activated carbon is used for high efficiency adsorption, water filtration, and biochar used for soil carbon sequestration, soil quality, improving soil quality, and contaminant remediation in soil. And activated carbon is harder and more durable and designed for heavy industrial use. Biochar is less dense and in some cases less mechanically durable. So now let us see, actually we have used one or two carbon-based photocatalysts. So before going to biochar, we have initially in 2007 itself, we have started using this activated carbon for supporting these photocatalysts as a support material for the photocatalyst. So we have prepared that activated carbon loaded zinc oxide or activated carbon TiO2 P25. That is titanium dioxide P25 is a special type of TiO2 having about 80% anatase and 20% rutile. It's specially marketed only for the environmental remediation. So we have prepared this activated carbon loaded TiO2 P25 and activated carbon loaded zinc oxide. And at that time, we have done the degradation of 4-amino-diphenyl. You can see this 4-amino-diphenyl degradation, and this 98% of AC zinc oxide is found to be most efficient when compared to the other activated carbon percentage of activated carbon zinc oxide. And this is actually a degradation of this pentafluorobenzoic acid and pentafluorophenol. And this is for pentafluorobenzoic acid. you know that one of my students was working in that alkali, TANPAC industry, where he had pentafluorobenzoic acid in the effluent, pentafluorobenzoic acid and pentafluorophenol in the effluent. Then we wanted to degrade that pentafluorobenzoic acid. We started using this 10% activated carbon loaded TiO2 P25 with two different wavelength, light wavelength. And we found that it is found to be 10% AAC zinc oxide TiO2 P25 was found to be most efficient in degrading pentafluorobenzoic acid. And this degradation can be monitored only by the formation of fluoride ions, because once pentafluorobenzoic acid is degraded and completely carbon dioxide, water and fluoride ions are formed, and fluoride ions can be reused. Then actually we have done treatment of an effluent. Actually, this is leather industry effluent containing a red, a dye, and the dye was degraded by using these 5 different catalysts: TiO2 P25, zinc oxide, fluorine doppler TiO2, zinc oxide nano, and activated carbon zinc oxide. We found that activated carbon zinc oxide is found to be very efficient. Even in 20 hours, 99 point, almost 100% degradation was occurred. So it's found to be very, very useful. The leather dye, dark brown MD, the leather dye, using the different photocatalysts. The same thing we have used in the pilot scale reactor also. We found that AC zinc oxide is found to be more efficient in degrading about 50 liters of the effluent within 6 hours completely. And another one is carbon quantum dots. This is also one of the very good material. Nowadays, the research is mainly focused on the carbon quantum dots. What is the specialty of the carbon quantum dots? It has many good characteristics. Actually, one of the unique property of the carbon quantum dot is upconversion fluorescence. Actually, when you irradiate a organic molecule or any fluorescent molecule, what will happen is, if you irradiate with 300 nanometers, you will get the emission at 400 or 500 nanometers. That is at the redshifted emission. Whereas in the case of carbon quantum dot, depending on the excitation wavelength, you may get a different emissions. So that is the specialty of the carbon quantum dot. Actually, when you excite at 300 nanometer, you may get at the 400 or 500 emission for carbon quantum dots. At the same time, when you excite at 600 nanometers, you get an emission at 300 or 350 nanometers. That is at the lower wavelength. High energy radiation is being, that is fluorescence. The conversion, fluorescence photoluminescence is upconverted, coming to the higher energy radiation. So this is possible with the carbon quantum dots. Actually, this is one of this one. Here it is the upconversion is not there, but 3% CQD bismuth oxybromide is found to be efficient in degrading the dye rhodamine B. And here you can see that titanium dioxide nanosheets with the carbon quantum dots, and the 10% of carbon quantum dot titanium nanosecond is found to be most efficient in degrading this rhodamine B. And what is the specialty of this one is, you can see the mechanism here, that we are giving 600 nanometer radiation for exciting the carbon quantum dots. So carbon quantum dot is photocatalyst, and the 600 nanometers you are giving, but once you give 600 nanometers, from the carbon quantum dot, you are getting 360 nanometer light. So this is called the upconversion fluorescence. So the 360 nanometer light is efficient. It is also capable of exciting an electron from the TiO2. That is, TiO2 requires only 360 or 370 nanometers for excitation. Band gap energy is equal to 360 nanometer. So when you give 360 nanometer, electron from the valency bond is from TiO2, valency bond is excited to the conduction band of TiO2, and that is used for the degradation of this one. Actually, what happened is, earlier I told in the modification of semiconductors, you have to use a metal doping or any other material for making them is a visible active. Whereas in the case of this carbon material, particularly carbon quantum dots, when you add quantum dots with the TiO2 or any semiconductor oxide, you can make them as visible active by using this carbon quantum dot, which is very, very cheaper and also can be used. So this is a specialty of the carbon quantum dots. Okay, that's all about this. We have so many other carbon materials. I want to tell something, 2 examples, carbon quantum dots and activated carbon. Now we'll see something about the biochar. So biochar is a carbon-rich porous material. How it is obtained? It is obtained only from the biomass. So waste biomass can be utilized for preparing the biochar. Biomass we are getting from so many waste materials, different type of waste materials. And here you can biochar, what is it? Characteristic of biochar is it is not having 100% carbon. It is having 65 to 80% carbon. And in addition to carbon, it contains so many functional groups and also contains some minerals like calcium, magnesium, and potassium, and all these things. So composition of biochar is not fixed. It depends upon the feedstock, wherefrom it is obtained. So it may be obtained from wood, or it may be obtained from the manure, or it may be obtained from the rice straw. So depending upon that feedstock and depending upon the production temperature, its composition differs. Actually, we have prepared the biomass from the lemongrass and also bagasse. And it can also be prepared from lemongrass, banana peels, orange peel, jackfruit, bagasse, so many. Any plant origin can be used for preparing this biomass. And from the biomass, you can get the biochar. So characteristics of biochar depends on the biomass source and also the techniques used to prepare the biochar. So as far as biochar is concerned, it's not a strong photocatalyst, but it acts as a very good material, excellent material, support material for other photocatalysts, creating the hybrid for enhanced performance. And what are that, how it enhances the photocatalysis? It provides a stable support because it has a porous structure, creates an ideal platform for dispersing the nanoparticles of the photocatalytic materials. So photocatalysts can be, can go and supported, stay in that pores and then it can react with the, toxic chemicals and degrade them. And it improves the charge separation because it has electrical conductivity, electrons from the photocatalyst, preventing them from recombination and making the photocatalyst more effective. So what is required in the three things we require: large surface area, reduced recombination, and visible activity. So here the increased charge improves the charge separation, increases the surface area, and also it acts as an electron reservoir because biochar can abstract the electron and then it can give it to other material. So this is called a synergetic effect. And that biochar can act as electron reservoir, can capture the photogenetic electron and transfer them to the surface to produce a reactive oxygen species, which are essential for the pollutant degradation. And another thing is the function station of biochar is pivotal. Actually, you can functionalize a biochar depending upon our requirement. It can increase the absorption capacity and the overall efficiency of the biochar photocatalyst. So the importance of biochar is known from this journal. Actually, there is a separate journal published for biochar. The impact factor is 13.5, very high impact factor. It is actually ranking at the first in soil science. So why I'm giving this slide is to show the importance of the biochar. There is a separate channel devoted for biochar itself. So any work related to biochar, if you have done, then you can publish in the biochar, which will be more visible and which can get more citations, because everybody will see only whenever they want anything about the biochar, they see this journal, then only they will go to the other journals. So that way you can get more visibility when you publish in the biochar. So what are the different sources available? There are a number of sources available. Some of the sources are given here. So this is nothing but bio-based utilization, harnessing bio-waste, how to harness a bio-waste or how to waste utilization can be done by using this one. So you can have agriculture biomass or municipal solid waste or food waste or marine sources, marine biomass or livestock manures or woody biomass, lignin and other things. All these can be used for preparing this, biochar. So what are the techniques? Different techniques are available. One of the technique is a pyrolysis. So in the case of pyrolysis, depending on the temperature, the morphology differs. You can see that pyrolysis temperature increases on this side. So when it increases, the crystallinity, carbon content, pore size, aromaticity or surface area increases. But at the lower temperature, the polarity and functional groups increases. So this is actually the effect of pyrolysis temperature on biochar properties. How the structure and absorption mechanism they vary. A shows an amorphous structure and B shows a chaotic structure and C shows a graphitic carbon structure at a very high temperature. So these are some of the different techniques. A number of techniques are available. The different techniques, these are some of the different techniques. One is a pyrolysis. This is a common technique everybody uses. Even when we want to prepare something, then immediately we go for pyrolysis. So pyrolysis is that depending on the temperature, we get 250 to 900 degree. Depending on the temperatures, we get different type of biochar with the properties, different morphologies. Another one is called hydrothermal carbonization. It's a very cost-effective method for biochar production and can be performed at low temperature. So we cannot give the detail about this one. These are the different methods available. And gasification is one of the very good method because by using this method, you can prepare the syngas. And also bio oil also can be prepared. I'll show the next slide what is the products by the gasification process. And this is a recent process. Tarification flash carbonization is a newly technique for biochar production. It employs low heating, referred to as mild pyrolysis, and oxygen and the other carbon dioxide present biomass removed using inert atmospheric air, and low temperature is used 300 degree at various composition procedures. So this is one which shows, pyrolysis by gasification process. So different type of materials or biomass feedstocks are shown here, and different that particle size, they may also differ depending on the particle size, moisture and other things, and depending on the reaction time and intake and the heating rate and the gas flow rate, you get other biochar characteristic, different type of biochar, and also you are getting bio oil and biogas. And this biochar, when you support with the catalyst, photocatalyst, the band gap varies. Actually, biochar is having not a strong photocatalyst, but actually is having the very low energy gap. So this electron can go to this semiconductor conduction band of semiconductor oxide, or it can, just like metals, it can form intermediate levels like this, and then produce a local trapping state and also mid-gap energy state. So these are some of these examples which actually this journal, the review gives a detail about all these things. So what are the applications of the biochar supported photocatalyst? A number of applications are there. We are not going to see all the applications. We are going to see only 2 examples or 2-3 examples of the wastewater treatment and also the hydrogen evolution reactions. So here catalyst can be used for organic synthesis. It can also be the BSP, that is biochar supported catalyst, can be used for organic synthesis, wastewater treatment, and toxic chemical degradation, and any toxic chemical, and also for superconductor applications and hydrogen evolution and antimicrobial activity. So these are some of these applications of the biochar supported photocatalyst. And this is a very vast area. What are the factors affect the biochar supported photocatalyst performance? Actually, when you go to this journal, each topic is dealt with about 2-3 pages. Feedstock and pyrolysis temperature, that also affect the performance of this biochar supported photocatalyst. And material band gap morphology, because band gap high or low, that also affect. And similarly, light source, intensity, temperature, catalyst dose. And here if you take a method also, reaction temperature, precursion materials, all these things. And modification also, and when heteroatom doping, you can have the phosphorus doping and nitrogen doped biochars are available now, and heterojunctions and magnetization. Magnetic biochar are being prepared nowadays. Suppose if you use Peresov Fe3O4, it is a magnetic biochar, because that biochar can be separated by using a magnet because it contains iron. Like that, the modifications, all the modifications, actually this journal, if you go to that chemical engineering journal, a review, it gives a detail about these factors affecting the biochar, this biochar supported photocatalyst performance. Okay, actually here we are seeing the morphology of the biochar prepared from different biomass. One biomass is Okara biochar. Okara is bindi, that is at lady's finger, and from that they prepare the biomass, and from the biomass they prepare the biochar. So this is called Okara biochar. And another one is, this is rice straw biochar, and the third one is rice husk biochar, and this is coffee ground biochar, and this is potato peel biochar, and this is shrimp cell biochar. So these are the sources of biochar. You can see how the morphology differs depending upon the feedstock that we are using for the preparation of the biochar. So now let us see some of the examples like applications. photocatalytic applications. You can see that lignin biochar, that is from the wood, the biochar material, it is actually an amorphous material. You can see that using the lignin biochar, that methylene blue degradation is done, and the photo degradation of methylene blue is done. So this lignin biochar is having the maximum efficiency, whereas this zinc aluminate, this is zinc aluminate, this is lignin only biochar. So this composite lignin biochar zinc aluminate bismuth phosphate composite is having the maximum efficiency in the degradation of the methylene blue. So this is showing the mechanism. This is a bismuth phosphate. Here you can see it's a bismuth phosphate and zinc aluminate. So this is a bismuth phosphate and zinc aluminate. Actually, the electron is excited from bismuth phosphate or zinc aluminate, and the electron is captured by this biochar, lignin biochar, and captured by the lignin biochar, and this is given to oxygen forming the superoxide radicals. So when the electron is captured, automatically hole is freely available. So this electron hole separation is very effective because of the abstraction of electron by using this biochar. So this is actually, this is a mechanism proposed for degradation of the methylene blue by lignin biochar zinc aluminate bismuth phosphate nanocomposite. And this is another one, porous graphitic carbon biochar. This is prepared from the rice straw. And you can see this morphology of this A and B is the same images of this biochar. And actually, this is molybdenum sulfide. That is graphene-like molybdenum sulfide. That's why just like graphitic carbon nitride, we say GC3N4. Here we call it as GMOS2, graphene-like molybdenum sulfide biochar. And you can see the TEM images of this and TEM images, and again this fringes. This is characteristic of molybdenum sulfide, and also this one. So here they have tested this degradation of tetracycline. TC is tetracycline. Removal of tetracycline in the presence of the different photocatalysts. You can see that this one G molybdenum sulfide is this PGBC. This is found to be most efficient in the degrading the tetracycline. Actually, this is a mechanism proposed for this one. As I told you earlier, this is actually acting as electron zinc. So electron is removed from the conduction band of this molybdenum sulfide, and that is given and then forming these superoxide radicals. And the holes are available for the oxidation of this, tetracycline. So this is another biochar. Graphitic carbon nitride is one of the very good material, GC3N4, graphitic carbon nitride. And graphitic carbon nitride and biochar obtained from the rice straw, and BC the biochar. M is as melamine actually G3N4 is obtained from melamine. So they given the ratio are 1/15. That is 1 part of biochar and 15 parts of melamine they have taken. That is found to be more efficient. This is a HRTM images of this 1/15 biochar A to B, and this is a DE is for C3N4. And here this is EDAX spectrum. And by using this 1/15 of BC by M, graphitic carbon nitride biochar, they have done the degradation of this rhodamine B. You can see that this one, actually 1/15 of this one is found to be most efficient in the rhodamine B degradation. And this is for methyl orange degradation. So two degradations are given. One is rhodamine B, another one is methyl orange. Again, the mechanism is a very simple mechanism. The same mechanism which I told you for the earlier one, that biochar is abstracting the electron and giving to the oxygen producing the superoxide radical and making the effective separation of the electron and the hole. This is another biochar that we prepared recently by using the lemongrass. So this is a lemongrass biochar, and then we treated the sewage water, and we found that 7% AB acted biochar zinc oxide sewage is found to be most efficient. And here also the mechanism is the same mechanism, simple. That is that abstracting the electron from this zinc oxide, conduction band of the zinc oxide, and giving to the oxygen, and this is separated producing these OH radicals. And another this one biochar is softwood pellets. They prepared the biochar from the softwood pellets and with the TiO2, the TiO2 SWP 700 and this is used for degradation of the phenol, and this is a dual function. In the liquid phase, they used for the degradation of phenol. In the gas phase, they used for the conversion of methanol into methyl formate. Actually, normally when you take any alcohol, it is completely oxidized, but it's selective oxidation. So they found that the TiO2, this TiO2 biochar is found to be selectively oxidized methanol into methyl formate, which is a very useful component in the industry and which can be used. So selective oxidation of methanol by gas phase and degradation of phenol in the liquid phase by doing the two functionalities. This is the TiO2 biochar, TiO2 SWP 700 biochar. And similarly, they have prepared this, biochar bismuth. That is biochar bismuth, one here. You can see that CB, three different temperatures. See, here you can see how the temperature affects. So one is prepared at 300 degree, another one is 700 degree, another one is 800 degree. They found that CBI 700 possesses the best degradation of sulfanilamide. It's a toxic chemical. So sulfanilamide degradation by using biochar with bismuth 108, biochar with bismuth 108 prepared at 700 degrees is found to be most efficient in the degrading this sulfanilamide. That's all about the photocatalytic degradation. And now let us see some of the slides for that hydrogen evolution reactions. So this is Fe3O4, perosulfuric oxide, Fe3O4, biochar. This is biochar. Actually here, the electron goes to the biochar, it accepts the electron. So this is a synergetic effect is, Fe3O4 biochar, synergetic effect is, illustrated in this slide. By using this Fe3O4 standard biochar, they performed the water splitting reactions. Actually, they used three biochar. One biochar from surface sludge, another biochar from softwood pellets, another from rice husk. So this is surface sludge, and this is softwood pellet, and this is from rice husk. They found that the hydrogen evolution reactions at a different one. They found that this one actually this is 2.5% is found to be most efficient. Here you can see hydrogen evolution. Sludge is 331, and the another one is that softwood pellets is 3385, and another one is 4162. So the biochar with the rice husk is found to be most efficient. This one blue is found to be most efficient when compared to the biochar with other material, feedstock materials. This is another photocatalytic hydrogen evolution of the biochar by using zinc ferrite. That's why I told you this is a magnetic biochar, because we are using iron, zinc ferrite. That Fe3O4 is also magnetic biochar. So zinc ferrite, three different, actually zinc ferrite composition is 1, 5, 10% and 20% they have used zinc ferrite in the biochar. And they found that hydrogen evolution reaction by using this one. You can see that zinc ferrite, 5% zinc ferrite and 5% biochar zinc ferrite is found to be most efficient producing the hydrogen, maximum amount of hydrogen when compared to the other ones. So the mechanism is shown here. Actually here what happened is the biochar abstract the electron. So just like electrical abstraction and giving to this oxygen and other things. And there is another compound that is called TEOO, triethoxy amine or diethoxyamine. Actually, it abstracts a whole. So this is a sacrificial reagent. It abstracts a whole, and what happens is abstracts a whole and also gets oxidized, because as far as hydrogen production reaction, only requirement is an electron, not the whole. Whole will affect that hydrogen evolution reactions. So whole should be captured and removed. So to remove the whole and capture the whole and remove it, for sacrificial agent of TEOA is used. TEOA is used, and then that removes this whole, so that electron is freely available for the production of the hydrogen. And this is another one called direction of 4-nitrophenol to 4-aminophenol by this the same compound. That is the biochar, bismuth, and iron composite. So we'll see that. So you can see that this is a reduction of the 4-amino nitrophenol to 4-aminophenol. I told you one of the application is a catalysis application. So nitro group can be reduced to the amino group. And during that, that other product are produced, that methane, carbon monoxide, and carbon oxygen are produced in this one. So these are the representation of this one. So these are that BCBF is nothing but graphitic carbon nitrate, that is biochar, graphitic carbon nitrate, this carbon, and B is a bismuth carbonate, and this cobalt ferrite. So all these things are made as a nanocomposite, and that is used for the production of the hydrogen. So that's all about this, application of the biochar in photocatalysis as well as in the hydrogen evolution reactions. So we have seen only the 2 applications in detail, and a number of applications are available. So as far as the biochar is concerned, it has a very good role in future. So the key roles of future is given here in this one. It can be used for wastewater treatment. Again, it is the same thing which I showed you earlier. Waste management, and this carbon sequestration, energy for producing the energy, for producing the fuel, and also for the soil improvement. All these things, these are some of these. And biochar can be produced by the different techniques here: hydrothermal gasification, pyrolysis, and gasification process. So this figure gives key roles of biochar in various applications. So in future, there is a potential application of biochar for the wastewater treatment, and also agriculture fertilizers, pollutant removal, and renewable energy generation like hydrogen production, and also more, approach to the waste management. You know that nowadays, whether it is a plant origin or marine origin or food origin, you get so much of biomass. So all the biomass can be converted into biochar, which can be utilized as a very good catalyst or supported catalyst. So the focus of the research is to prepare a bio-waste derived biochar, multiple functionalized biochar, biochar tailored metal oxide, and to study their utilization in various fields of applications. Actually, I'm giving this only because we have done our work is on biochar is very limited, but the biochar nowadays is getting more focus, and is easily available from various sources, and this biochar can be used for various applications. So the future research should be more focused on the preparation of different kind of biochar. One of the very good advantage of biochar is it can be tuned for that required applications. So depending on the feedstock, depending on the temperature, you can prepare a number of various characteristics of a biochar. That is possible. So this is the one. So that's all about this biochar, role of biochar in the photocatalysis and electrocatalysis. So thank you very much. And this is the one which I used to show in all my lectures. This is our place called Port Novo. Very near 7 kilometers from Chidambaram or Annamalai University, where this Annamalai University Center of Advanced Studies in Marine Biology is located. And this is the second largest mangrove forest in that world. And this is the one is one of the ecotourism spot in South India, and having number of birds, 177 species of birds are recorded. And this is the one which saved the people during the time of tsunami who are living in that area. So thank you very much. And thank you. This is actually, I am from Chidambaram, and this is Lord Nataraja temple, the golden roof of Lord Nataraja temple. Inside the golden roof, the Lord Nataraja, he is there in the dancing posture. So thank you very much. So once again, thank the organizers for this one. Thank you.
Thank you so much, sir. It was really an insightful lecture. And I just would like to introduce your detailed CV, which I was supposed to introduce in the beginning of the lecture. I apologize, sir, due to some miscommunication, I couldn't do that. But now I would like to highlight, we are privileged to have Professor Swaminathan, a visionary scientist whose contributions have profoundly shaped the scientific community. Professor Swaminathan completed his MSc from Annamalai University in 1972 and his PhD from IIT Kanpur in 1983. He has over 40 years of teaching experience and 46 years of research experience, and retired as professor and chairman of organic chemistry at Annamalai University in 2010. He later served as a CSIR emeritus scientist and is currently a visiting professor at Kala Salingam Academy of Research and Education. He has guided 20 PhD scholars and published 298 research papers with more than 12,000 citations and H index of 56 and an I-10 index of 324, along with one book and several book chapters. His research focuses on photochemistry, nanomaterials, photocatalysis, fluorescence spectroscopy, environmental and energy-related applications. He is a fellow of Royal Society of Chemistry and has been listed among the top 2% scientists globally by Stanford University since 2020. That is the greatest achievement. His major awards include the Tamil Nadu Scientist Award, CRSI Bronze Medal, and multiple Lifetime Achievement Awards. He has also held key academic positions and contributed significantly to scientific societies and journal editorial boards. The insightful lecture on biochar was truly commendable, highlighting its transformative potential in sustainable environmental and catalytic applications. Now, I would like to give the key takeaways from the lecture of Professor Swaminathan. So it was really a very great opportunity to listen to you in this conference, and you deeply explained the importance of the application of biochar, which is produced from bio-waste, in the photocatalysis and electrocatalysis, importance of band potential of semiconductors in splitting of water. You also explained the advantages of carbon-based materials as good adsorbents. You talked about degradation of leather dyes using different photocatalysts. You also highlighted the unique properties of carbon quantum dots, such as upconverted photoluminescence behavior, photocatalytic mechanism by carbon quantum dots, and you also explained how biochar enhances the photocatalysis because of a high surface area, porous structure, and rich functional groups. In photocatalysis, biochar improves the light absorption and facilitates charge separation, reducing electron-hole recombination. In electrocatalysis, it enhances the electrical conductivity and promotes faster electron transfer, so improving catalytic efficiency and reaction rates. You also explained multiple applications of biochar supported photocatalysts, especially you highlighted on waste management and production of energy. So overall, it was a enriching experience for all of us. Thank you so much, sir. Now, I would like to invite, if anyone has any question, they are most welcome to ask. Thank you, sir.
Yes.
Hello.
Hello.
Sir, you have given very nice talk on this biochar can be used for the photocatalysis, okay, and electrocatalysis.
Yes.
Just I want to know, this is the one of the application that you are using biochar.
No.
On the other side, also, biochar can also be used for the removal of heavy metal ions, no?
Yes. Actually, it's a good adsorbent. You can use it,
Yeah.
but you can make use of this one for this even so many applications. Only I have given only two kind of applications now.
Okay, and how you have, it is obtained from the waste of the agriculture, and therefore it is a very good material for the maintaining sustainability and for
Waste
the
management.
circular economy.
Yes.
Circular economy can be maintained for this. Okay, useful material. So which material you have used for making this biochar?
Actually, one of the material we have used is lemongrass biochar and bagasse recently.
Okay, yeah.
But the bagasse is plenty, available in plenty. All the sugar plants, they are, giving bagasse.
Yeah.
So you can get
Yeah,
bagasse as well as a lemongrass. You can get, or even you can actually. There are so many papers on banana peel, orange peel, and this even jackfruit peels and all the biochars are available. So any origin can be used for preparing the biochar.
Okay, yeah. So yes, good. Very nice presentation, sir. Thank you.
Thank you for the opportunity given to me. And
Yeah.
opportunity, with the opportunity, we are able to meet all of you. Thank you very much.
Yes, sir.
Thank you.
Yes, sir. Okay.
So I've given so many references in my this one talk. The review references are there, so they can be referred to get more information about this biochar supported photocatalyst.
Yeah.
Thank you. So, shall we conclude the session, sir?
Yeah.
Okay, thank you.
Hello, another lecture is on the Google Meet.
Okay. So that's it. I mean, thank you very much.
Yes, sir. Yes, sir.
Thank you. Sir.
Hello.
Uh,
Hello, Bishpriya madam.
Yes, yes, sir.
Hello, where is Deepika madam?
Yes, sir. I'm Dr. Pooja Pillai. Yes, sir. Yes.
Okay,
This lecture
conclude this
is
session.
yes, 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 yes. Thank you very much, Professor Swaminathan, sir. Your lecture was very enlightening, and we are very grateful for your this invited talk. Thank you very much. I also thank Dr. Gunale sir for giving this opportunity to all the participants and presenters. Thank you very much, sir. Now we'll move on to next technical session for today's conference. Thank you.
क्या खाऊं यार, मुझे समझ नहीं आ रहा है। दाल चावल अभी खाऊं कि बाद में खाऊं?
बाद में इसलिए रात को खाया।
This technical session is over now. Thank you very much. We will move on to next technical session.
येते का? येते ना?
There are four important things. Like this design. Nature, technical regulations, researchers, it is the one thing. And there are so many other things to produce different kind of so this is more important thing. We have very possible.
So not audible, no?
It is like Ready? Operation 60 what if product is present. What has it done? That's done to concern the skills and professional. We are in the 447. Because we are fine. All right. You have to make a very page. Yes, yes. Can we still use into layers to this kind of so now the you can harvest that is splitting. Better. So whatever you want, focus. It's we take her. She can see her. From that she can yes. Put it in a what did he see? And actually now it began this is very right. And then so they can use that utility. Let really use hydrogen for only for production. So then so you see what is the fuel. You can select 30% part of it. Okay. This is what is your approximate mileage is not cost. So what is here? And the production cost 800,000 almost. So we need to consider the cost of production, cost of transportation, cost of cost and the profit will be of actually when student pressure kind of there's a maybe a high in fact it's not to release outside plus it's one of the legends. Another is the production of hydrogen is all eating is transformed with but see, I don't know about it's that also. So let's see here. Empty center. Empty center that will compress hydrogen in three. So what is very well can be compressed in this cylinder in approximately 300 degrees. Hydrogen that is also said. So, one comes to the solid or liquid organic materials. That is so we're going to discuss about that energy material. Hydrogen. This took time. Before this one, it is very clear. Another hydrogen is very clear. I want this to be certificate. Solid hydrogen storage premium. Yeah. Hey. So, because I am the rate, I am the rate. Expensive. We can go. And this also is so then we estimated. Then 3 seconds. Just a hydrogen is a solid state hydrogen. That is, then we can avoid the fuel station. Like this fuel. Lead it to that, right? Okay. So here, there is a position. So this is there is function. This is a Jason. Change the mind. Writing more different parts of it, trying to create to then another will be loaded. So this is not any. Okay, the first one. Medicine take for balance. Third one. Here, get the cooking list to one but material is and what is okay. He has been used the high and the get the 0.45 result and get I think that is the one you highlight. Check the SI. Okay, even different we also for the interval part. But you go over the time. Better. Before that, you can also put them off and then them off. Okay, this is the melody. And after that, there is no impact. Then after that, so magnesium oxide is really kind of clear and already you can is it? As it's the restricted activity that I have written. Second, okay. Here. This right you the cardinal cost. However, the cardinal is take the height. This. What is the good term? It's not.
ये बैठ रहा है कि ये बैठ रहा है कितना कायचं आहे म्हणजे
The side giving both sides distribution getting in both sides so Okay. Your age is that's it. That's really the time very much our system. Approximately right starting. So, this is the valuation of empty focus. That is a pure one. Stage one. A huge amount. That's up. So, we did see that. One second. Everyone. So you can see here, looks like how it died. So, it's not, I didn't.
रोज रोज 3 दिवस राहू दे 12 तारखेपासून आजच्या तारखेपर्यंत विचार करून रोज आपण प्रत्येक
Okay. Let me back. So the second part is that we have. Okay, here. So here. So this There will be some evidence to do. When you provide the instrument of creates the direct cycle. So, say this we are using slow to big time. Let's see this so what I think for permission it's some temperature required synthesis to some new kind of or loading some facility to be out. Structure is about hydrogen is right. So in this case, the strong society is so the is electrons. The load can see that these peaks without respect to the target. How does it is it when you can see big pumps like yeah, you can see. Yeah, you can see. The blue stop. Okay, right? Yeah. See this. Okay. So that is so there's no where is from into the versus 98% tolerance. So, in a way, so 49. Nine percent of them. Is what has been called. So this is. Yeah. Registration. But that is is it a medical condition? Can see. Some. These are observed notification. And another say thanks to my professors first time. Those are producer of TV. Yeah, just some like publicity. And he's a professor. Experience now is like so okay. Thanks to you. So, Santosh Vedas, are you here? Yeah. Yes, okay. Madam, you know, I was saying yeah. Somebody, so we start second.